Good morning, everyone. So, thanks for the introduction, ma'am. So, I'm Vaithinathan. So, I'm basically from Tamil Nadu, Pondicherry. Okay, so I did my bachelor's in electronics and communication. Then I did my master's in green energy technology. Then I moved to PhD in Hong Kong. I started to work on the semiconductor devices and materials. So, um, before going into my topic, I wanted to bring to your attention like what are all the energy technologies available in this society right now. Okay, so every one of you know that we have solar cells like photovoltaic technologies, right? So what they do is that they observe the light from the sun and then they convert it into energy, right? So that's one type of energy conversion. And then we have what wind energy, right? So you will have all seen around the coastal areas we have wind turbines which converts wind energy into electrical energy, right? So and then hydro energy which converts water power into mechanical power into electrical conversion, right? So these three are the major contributors for all types of renewable energy technologies available in the society right now, right? So other than this, there are many other energies in the society available around you, right? So these energies are also being wasted like everywhere to the surroundings. So how to use them is what we are going to talk today. Okay. So I focus mainly on thermoelectric technology. So what is thermoelectric technology is where like see in your daily life you experience when you wake up in the morning you drink coffee tea, right? It's hot, you like it hot, right? So where is the heat coming up and where is the heat dissipated to? It's being dissipated to the surroundings, right? This is called waste heat. So it's being dissipated everywhere. Even human body releases heat, right? So I'm developing technology, material technology to capture these types of heat, not only from human body, we also capture from industries and also from motorbikes, bus engines, and then convert them back into electricity for usable process. So this technology is available since 1857, okay? But this did not get mature like the solar panels you see in every day, like the wind turbines you see in every day, okay? So because these are expensive materials and they are toxic and not enough people to work on.
Sir, slides
So
are not changing, sir.
I did not start.
Sir,
I did not start it. I just give the introduction. I will change
sir,
it. Wait a
excuse
minute.
me, sir.
Okay. Yeah, I
Sir,
can.
slides
You
are
can
not
hear me.
changing, sir.
Okay. I think now it should be okay, right? Do you see it?
Yes, sir. Now it's okay, sir. Yes, sir.
Okay. Okay. So yeah, just give the introduction first and then go for the changing. Okay, so how this technology work is like we apply heat to any material, like two different materials. So for example, take copper. So like let's come consider this is copper, okay? This is tin, SN like tin, right? So you have two metals and then you are connecting it with the interconnect, okay? So and then you apply heat here and then what happens? The electrons in the materials get extra energy from the heat you applied and start to move towards the colder end. Okay, so when the charges move from one place to another, then there is a voltage developed, right? So this voltage is called Seebeck voltage. Okay, so Seebeck voltage, right? So this process is being used to convert heat into electricity. So the voltage we develop, we capture it and store it in the battery for later applications. So this is one type, and the same thermoelectric technology can be used also for another application, which is refrigeration, like you use in your home every day, right? The fridge. So the same thing can also be used here. How it is being used? Here you apply the heat, here you apply the cool energy or the electric power. You apply the battery power and then it produces cooling effect on one side and then the heating effect on the other side. So these are the two types of phenomenon happening in the thermoelectric technology, okay? So what we do in my lab is we develop materials, sustainable sustainable materials for these applications, okay? So where did I get the motivation to start this work is you can see in your daily life. Heat is available in thermal power plants, nuclear power plants, vehicles, and then like waste, garbage burning places, and then factories like cement factories, glass factories, right? Also, the natural gas industry is also developed. So you can see there, like, just consider, about the Carnot engine efficiency, right? So Carnot engine can be only like 75% efficient. Where is the remaining 25% going up? So the remaining 25% is being released to the environment as heat. So if you just capture this heat, like 1% of the heat released to the environment, you can power the whole city for one day. So you can see how much energy is being wasted in every day. So what we do is we develop these materials and the devices, right? So how can you check the efficiency of these devices and material is using the term called figure of merit. Okay, so figure of merit is the categorizing point. Like if the figure of merit is less than one, the device is very poor. If it is over one, it's good, and then if it is over three, it's best. So for each category, so we use for different applications. So for example, if we have a material with figure of merit 1, then they are being used for RTGs. What is RTG? You know about interesting fact, like in NASA, in, I think I remember, in before I was born, like 1963, there was, oh sorry, 1977, there was a space probe Voyager 1 and 2 were sent, and they are still working. They are not using batteries or solar panels, because as you go deeper into the space, the all the light is disappeared, all the heat is disappeared. So how can you power an electronic device? So there comes our thermoelectric generators. So this produces, absorbs the heat from radioisotopes like uranium, plutonium, or thorium base. When the heat is being generated from the radioisotope, these materials develop the energy required for the electronic device to operate. Okay, so even in our Chandrayaan 2 mission, so our rover got damaged in the day 2 because we don't have any TEGs in the Chandrayaan 2, so that we can wake it up next day. So in India, we are still working on this technology where we will use for space and other applications. Okay, so if the figure of merit is 1, then we can go for space or wearable applications. So if the figure of merit is 2, then you can use it for automobile industries. So the cars like BMW and Audi, they use this technology to convert the heat produced in the engine back to the battery so that they can operate the air condition or the light inside the car or the bus. So if it is over 2, you can use for replacing the thermal power plants, and if it is over 3, you can use for heavy industrial applications. Okay, so I said figure of merit, right? So how is this figure of merit is being calculated? Is using the parameters Seebeck coefficient, electrical conductivity, and then thermal conductivity. These all with respect to the temperature. Okay, finally you will calculate the device efficiency by the ZT cases, putting them in the formula here. So usually all the commercial products available in the market uses only like 5 to 6% efficient. So the target to achieve is over 20% is what the research is happening in the world. Okay, so what is the problem really with the thermoelectric materials and devices is, see, I said like we have Seebeck, electrical conductivity, and thermal conductivity, right? So you can see from the formula, the numerator is Seebeck and then electrical conductivity, right? So if the numerator is very high, then the ZT can be high. If the denominator is very high, then the ZT will be very less, right? So, but you cannot change them, because when you try to increase the Seebeck, the electrical conductivity will try to fall down. And then when you try to decrease the thermal conductivity, then Seebeck will try to fall down. So these are all like a loop. They are all stuck inside one circle. It cannot move, it cannot improve. So in our lab, what I was thinking is like I wanted to break this relationship. So how we break this relationship is purposely inducing defects. You know about silicon, right? Silicon is having a crystal structure, right? So if you have defects in the crystalline silicon, then you cannot have a perfect electronic device. But in the reverse case, in thermoelectrics, we need to have defects to have a higher ZT value over 3. So I work on inducing defects into these lattices, and then so that we can increase the ZT. Okay, so how we do this is using these 5 strategies. Okay, so I'm going to tell one by one how am I going to do this. Okay, so first what I did is I induced defects using rare earth dopant. You know what is rare earth dopants, right? Rare earth materials. In the periodic table, you can see in the bottom line actinides, lanthanides, right? So I'm using lanthanides lanthanides to use the as the dopant cases here. So for that case, I use alloys like tin zinc antimony and tin selenide. And then we also do interfacial engineering and then composite engineering and then 3D printing of materials. I'll show you demo one by one. Okay. So first let's move into the defect engineering case using lanthanides. Okay. So you know first First of all, when thermoelectric materials were invented, so they were using lead, lead type of materials, tellurium type of materials, and selenium type of materials. So you know the toxicity of lead, right? Lead is a heavy metal. So if you are having lead or mercury in any of your electronic device, you cannot sell them in America or European countries. So people started to slowly reduce the use of lead and tellurium and selenium cases. So we go for sustainable, what is available around us in a larger quantity and lower price is what our target. So we go for zinc antimony based materials to develop thermoelectric devices. Okay, first of all, what should be the characteristics? So, for example, if you think about a food, it should have a good taste, it should have a good look, and then it should be hot, some characteristics, right? So, likewise, in thermoelectric materials as well, we have some characteristic required. So, the crystal structure should be complex as possible. What is mean by complex is like the crystal structure should be very complex, not like a free structure. Okay, so you can see the crystal structure here is rhombohedral and then it is very highly packed. So that type of structure will help for higher ZT. So then you should follow phonon glass and electron crystal model. What is phonon glass and electron crystal model? Is phonons are heat elements, right? And then electrons are crystal, I mean crystal or periodic arrangement, right? So if when you apply heat to a glass, what happens? Just consider early morning if you go to a tea shop and then you drink a tea, they give you tea in glasses, I mean made of glass, right? Why? Because it doesn't conduct heat and then you can hold it for a longer time. So that's the point. It should not conduct heat, I mean as phonons, like a glass, and then it should conduct electrons like a crystal. So this is the model you should consider for choosing thermoelectric materials. So then what I do is I dope the rare earth element because rare earth elements have f orbitals in them. So when you dope it, then they induce defects. So rare earth elements are bigger. Okay, just consider the atom is too big, and then you are doping it inside the lattice, and then it will kick out one zinc atom and then go and sit in this place. So what happens? There is a defect formed. Okay, so that's what I show here. We are having a rare earth element, and then I'm doping it inside the crystal lattice. It go and sit here. It kick out a zinc atom, so that there is a vacancy there. Wherever there is defects, then they become a charged defects. So in case of silicon, like if there is defect, the material doesn't work, right? But here when we create a defect, what happens? It becomes an electron or hole. So we call it charged defect. Okay. So how do we see it? So if you take a piece of silicon and then you want to measure how many electrons or holes inside